now? Can you see? Can you see it?
Yeah. Yes.
Sorry, can you see it?
Yeah, we can see, but I'm not sure why we can't see full screen. Give me a second. Yep. Yeah, no, it works. Thank you.
Yeah. So is it okay now?
Yeah, go ahead.
Okay. Perfect. Yeah. Okay. So, hello everyone. So I'm Mohammad Abdulaziz from TU Munich. Today I'll be talking about my work in collaboration with Petar Lamis and Lucas Kola here, who are also from here at Munich, who are working here at Munich, on developing formal semantics for languages to represent planning problems and their solutions. As you are all aware, definitely in this workshop at least, that AI is proliferating into many safety critical applications, but a big challenge for that is that some AI algorithms and formalisms are not theoretically well understood, and even if they are theoretically well understood, their implementations are very difficult in a way that makes the theoretical understanding not very transferable. So I guess the the better known part of that is for popular machine learning approaches like deep learning, for example. So it's kind of well known that the algorithms are not theoretically well understood, and it's complicated to even verify just single deep neural networks, as the last speaker was describing. But for symbolic AI methods, this is also the case. So, and I will be talking specifically about planning. So planning is a symbolic AI method or methodology, which has many safety critical applications like autonomous driving and aerospace applications, for instance. And in general, the trustworthiness of planning systems is limited due to many issues.
Okay,
example,
Leo, I'm coming.
Sorry?
Oh. Sorry, I wasn't muted. My child has just shouted. Sorry about that. I thought I was muted.
Okay. Yeah, it's fine. Yeah. Yeah. Sorry. What was I saying? Yeah. Okay. Anyway, yeah, I was saying that planning is a symbolic approach to AI, which has many applications, but there are many problems also to its wide trustworthiness, for example. So trustworthiness is not widely accepted. For example, the algorithms, effective planning algorithms are combinatorial in nature and have very complicated proofs. And also a challenge with some planning formalisms like probabilistic planning is that we don't even know what safety criteria to verify, let alone how to verify them. And another challenge, which is more relevant to this talk, is the semantics of languages to represent planning problems and the fact that they are complicated. In particular, there are multiple definitions of semantics of planning languages, and they are a lot of the times ambiguous, where your interpretation basically can mean that a certain plan is valid or not. And today I'll be talking about how to address that last problem of the semantics of planning languages by formalizing the semantics of the main planning language, which is PDDL in an interactive improver. And let's go. So PDDL stands for Planning Domain Description Language, and it's the language that is currently used by for all planning competitions and most planning systems. And it was introduced in 1998 by McDermott and others. And later it has been extended to include richer features like actions with duration, like dense time duration, and continuous effects and hybrid processes and events, which are really expressive features, where you can have a differential equation specifying an action, for example. And very generally speaking, PDDL is a schema-based language. So in this language, a planning problem is defined as a domain file and an instance file. Okay, so I will just try and give you a quick overview of the language now. So a PDDL domain file gives the first order model of the system in which the planning is supposed to happen, or the scenarios in which the planning is supposed to happen. So this is And in its simplest form, a domain basically has a type hierarchy of the objects you would expect to see in this scenario. So for instance, in this slide here, we see a snippets from a planning domain for just robots and balls and a robot that is supposed to move the balls. So here we have two types, ball and robot. And the domain also specifies a set of sorted first order predicates, which can describe the state of the system. So for example, here we have a predicate holds, and it takes two arguments or two parameters, R and B. R is a robot and B is a ball. And lastly, it also specifies a set of actions schema, each of which takes parameters of certain types. Like for example, here, this action throw takes parameters of type robot and type B, and each of them has preconditions defined in terms of the predicates that are also from the domain. So for example, here, hold is a precondition of that action. So R has to hold B, and its effect is also in terms of the predicates. So here, the effect is that R no longer holds B. Okay. A PDL instance, on the other hand, enumerates a list of objects, enumerates some objects that occur in a particular planning scenario. So for example, here we have a specific scenario where we have two robots, and it also specifies a specific initial state in terms of the predicate instantiated with instances. So for example, here we have that robot 1 holds ball 1, robot 2 holds ball 2, or ball 1 or ball 2 should also be some objects in that instance. And the goal formula, which can be a first order formula in terms of the predicate and the objects. Okay, and the goal formula is basically what the plan should achieve in the following sense. So a plan is a list of instantiations of action schemata using objects only from the instance. Okay, so for example, you can say throw R1 B1, throw R1 B2, etc. Just a list of instantiations of those actions. And basically, the question of the semantics of PDL is basically what does it mean to be a well-formed problem or plan, and what does it mean to execute an action, and what is a valid plan? As in, what is a plan that solves a problem? Okay, a given problem. So now that I've introduced you PDL, I will introduce you something called automatic validation, which is important for planning. So basically, a validator is a program which, given a PDL problem and a sequence of actions, identifies whether the problem and the sequence of actions are well formed, and whether that sequence of actions is indeed a solution for that problem. And this needs to be done automatically by program, because typically problems and plans are very large and beyond human abilities, and also in planning competitions you have hundreds of planning problems, so it's impossible for someone to just take all the solutions from the different competing systems and then see whether they solve the problems or no. So there are already two existing plan validators. One of them is called Val, which is the more popular one. Another one is called InVal, and I will just quickly review Val to give you an idea of the problem that we're solving. So Val is implemented in C++, and it has good running time and memory performance, and it supports all mainstream features of PDL and advanced features as well. And and the most important part here is that it is effectively what defines the semantics of PDL, at least for the purposes of the international planning competition. So there is no formal specification of what PDL is other than the C++ implementation of Val. And this is problematic because C++ is very low level, and accordingly, it's very hard to understand what the semantics actually are, especially for advanced features. And also, one cannot prove much about this the C++ code. For example, it's not easy to show that the semantics represented by this C++ code have certain sanity checking theorems or sanity checking properties, for example, that you would expect your semantics to have. So this is the problem. And I'll just show you an example right now with a very simple part of the semantics to show you the extent of that. So for example, the most basic part of the semantics of PDL is specifying how an action affects a certain state if it is executed in that state. So for example, here we have an action 5, and we execute it at state X. Okay, so mathematically you would just represent this like that. In the and the meaning of that is the following. So you have an action pi that falsifies some propositions, to which I denote by pi d, and it also makes certain other propositions, which I denote as pi a, true in the next state, okay? So mathematically, you just represent executing that action or the effect of executing that action as x set minus pi d union pi a, okay? But in C++, this is implemented in that way. And this is basically the only formal semantics that we have of PDDL for the specific part. So it should be clear now that for more involved parts of PDDL, having C++ as the semantic specification is not a good situation. And in fact, the worries that I've been discussing are not just theoretical worries. For example, during this project, my co-authors found that for val, for example, if you give it this like this atomic predicate and this atomic predicate, it doesn't differentiate between them because it has a bug in concatenating, interpreting concatenations of strings. And also the other validator inval, which is implemented in Lisp, does not terminate if there are cycles in the type hierarchy, even though there is not an explicit ban on cycles in the type hierarchy. So the method or the solution that I'm proposing to resolve that is as follows. Basically, specify the semantics of PDDL in interactive theorem prover, and then specify an implementation also in the interactive theorem prover of a validator. Okay, so this has to be an executable and an efficient validation system, and then prove that that implementation is equivalent to the semantics or implements the semantics. Well, I think you all know what an interactive theorem prover is, but this is just a snippet of Isabelle Hall, which is the system that I'm using. So basically, this is just a proof that the square root of 2 is not a rational number, and this is the proof. So this is the statement, and that's the proof. Okay. Now, why is this approach a good solution? The main reason is that the languages of interactive theorem provers, like Isabelle, for instance, basically resemble pen and paper mathematics. Okay, and the specification in these languages does not have to be executable, which gives rise to a much more concise and understandable semantic specification. Another thing worth mentioning about this method is that the implemented validators, they don't have to be they don't always have to be of very bad performance. In fact, you can have an implementation that is as low level as you want and as optimized as you want. But of course, the more optimized your implementation is, the more difficult it is to prove it equivalent to the semantics. Also, an advantage of this is that you can very easily prove a theorem about your own semantics, like a sanity checking theorem, to make sure that the semantics have the expected properties, basically. And this cannot be done if you specify your semantics only as a piece of C++ code. Now I'll try to give you an overview of the whole approach by showing a simple example. So I will show you how to formalize the abstract syntax of an effect of an action, and then the semantics of what that means. And I will just show you how to use Isabelle's abstract algebraic data type to represent the syntax tree first. Okay, so the first syntax element that I formalize here is this is a predicate. So this is a snippet from the BNF of PDDL that was published by someone called Kovacs in 2011. So to specify that syntax element in Isabelle, it's pretty straightforward. We just define a data type predicate, and then it just has a name in it, which is a string. Then to specify a slightly more complicated element, which is an atomic formula. So in the BNF, an atomic formula is either a predicate applied to a list of atoms, or an equality of a list of terms, or an equality between two terms. And then here we have that atomic formula. Again, as you can see, the data type reflects that in a very straightforward way. And lastly, to specify the syntax element corresponding to an effect of an action. Again, this is the BNF specification of what an effect of an action is. So here we have two kinds of effects, either an atomic effect or a composite effect. So an atomic effect is either a negation of an atomic formula or an atomic formula, and the composite effect is either an atomic formula, an atomic effect, or a conjunction of a list of atomic effects. So that's represented here in this way in Isabelle's as an Isabelle algebraic data type. So here we have, it's represented in a way that's slightly different from that. So here we have an effect that has a so-called add and so-called delete. And the add is just a list of atomic formulae representing a conjunction of atomic effects that are all positive. So they will be true in the next state. And this one represents a list of atomic effects that are all negative. So negations like that. So they will all be false in the coming state after executing the action. After specifying the syntax, abstract syntax tree, we specify the semantics, of course. So to specify that is the syntax element that I showed, which is the semantics of execution that I showed you earlier. You just do that. You just specify it like that in Isabelle. So as you can see, it's very straightforward. It's not much more concise than the dozens of lines of C++ or the much longer the specification of what action execution is. After specifying the semantics, we specify an implementation. So what that means is that we replace unexecutable constructs with executable ones and replace inefficient data structures with efficient ones. And we can do some steps manually and some steps automatically. So for example, to define action execution, so this is the abstract, this is the semantics of action execution, and then we specify that as a first step. So this is like a list implementation of tests. So it just is implemented as a fold. And this is done, we do this manually, and then we can get also from this one to that one, which is an efficient implementation of sets as trees. This is just generated code from Isabelle using the container framework by Lamy and Lochbihler. And after you specify the implementation using this refinement approach, by refining basically the semantics step by step until you reach as efficient of an implementation as you want, you prove that the executable implementation is the same as the semantics in a theorem, basically. So this is basically the process. So far, I've only discussed very elementary features of PDDL to show the whole process and its merits. But now I'll just briefly discuss with you some more advanced features of PDDL, but I won't be able to go into the details of how we formalize them. But I hope that this would entice you to read into how we did that. So there are other relatively more advanced features of PDDL whose semantics formalized, like type hierarchies and temporal planning, where the reduction in the complexity between by comparing the C++ DAL code versus the Isabelle formalization is much more drastic than the example I showed you. And I'll give you, I'll just talk briefly about the most interesting one of those features, which is temporal planning, which are basically planning problems that have a notion of a timeline. And I'm not here telling you what is a timeline on purpose, because it actually was not, has not been clear, at least for a while, and I will go into details. So let me just give you a quick introduction of what these actions look like and what these problems look like. So an action from a temporal planning problem, which is called a derivative action, looks like the one shown here in this example. So here, this is an action that models a passenger. So these are the parameters. A passenger that enters an elevator at a certain level. Okay. So notice that this action has a duration or a duration constraint in particular. So here we say that this action, for example, has to take less than or equal 1.5 seconds. And it has a precondition, which is that at the beginning of the action, the passenger has to be at that level, and the elevator has to be in that level. And another kind of precondition, which is which I will refer to as an invariant. So this is this precondition has to hold throughout the whole execution, but this one has to only hold through the start. So at start, both the passenger and the elevator have to be at the same level. Throughout the whole execution, the door has to be open. And the effect of these derivative actions can take place at the beginning or at the end of execution, or both. So for example, here at start, once you start that executing that action, the passenger is no longer at the level, and at the end of it, the passenger is in the elevator, all right? So in this formalism also, this is how a plan looks like. So it's not just a simple sequence of instantiated actions. It is basically a schedule of actions that is equivalent to a Gantt chart, where every action is given a starting time point and a duration of its execution. So for example, here this plan shows how two passengers can use the two elevators to change their levels. So the first one is at level 0. So this is the passenger that is at level 0, and the other one is at level 1. And they both basically want to switch levels. using two different elevators. So as you can probably see now, these plans introduce a lot more complications. So for example, they give rise to parallelism of action execution. Or for instance, the first open elevator action, this one, will have to execute in parallel to this enter elevator action, because this one starts at 0.75 seconds and this one starts at 0 seconds, but its duration is 1 second. Also, another challenge with this kind of planning problems is what does it mean? What is the right model of time? Is it real? Is it rational, etc.? So the current way these semantics are modeled in val is so time is represented as a floating point number, and there is a minimum non-zero separation between all the time points in a plan. Otherwise, and the user has to give that minimum separation for every plan the user wants to validate. Otherwise, this might lead to a plan being rejected just because you specified a very small epsilon. Also, the semantics of actual plan validity is basically an algorithm to validate Gantt charts, and that's all. So it's more than 1,000 lines, more than 1,000 lines of C++ code. In Isabelle, on the other hand, you can specify the semantics in a much more much cleaner way and a much more concise way. So for example, time is a rational number, and the semantics is just of what a valid plan is just some high-level specifications. Like for example, every action has to have its preconditions ready before its execution starts, etc. And the semantics overall are less than 100 lines of Isabelle code. And then we derive an algorithm implementing these specifications, which is the same algorithm as the one that is implemented by Val, which is the Gantt chart validation algorithm. So this was basically an overview of the features of PTDL and why would you need to formalize them. So I would just like to, before closing, to just say two things. So the experimental performance of our validator is worse than Val, the C++ version, but it's not. It's all within one order of magnitude, and it's all, as you can see here. Like the maximum running times for all the different domains is like 5 seconds. This is the worst thing. Well, for example, the Lisp validator in Val has much worse running times than our verified validator. So practically, this is not bad since validation can be done, like as you can see, can be done quickly anyway. Lastly, I would like also to point out that we proved some sanity-checking theorems for the validation, like for example, that a well-typed plan on a state results in a well-formed state, where a well-formed state is a state that doesn't include contradictions. So that is my talk. So just to conclude, as the points that I'm trying to convey here are that the semantics are much more concise if they're formalized in a theorem prover than the current situation where they are just the only formal model of them is just a C++ implementation, for instance. And the performance does not necessarily need to suffer if you're going to derive a validator from that, and you can prove sanity checking properties of these semantics, which gives you better confidence in them, especially for more advanced features. And in the future, we would like to focus on continuous change, or for example, an action effect is an ordered differential equation. And that's all. I look forward for questions. Thanks for your patience.